online today. So my name's Killian Stenning. I'm a research fellow at Imperial College London, and I've spent maybe the last 3 or 4 years of my research career looking at neuromorphic computing systems, and in particular nanomagnetic systems. And so today I'm going to give you a bit of an overview of the types of computing that we can do with those systems and try and link that into the general theme of this conference. So I'll start off just by giving you a bit of a background, and we've had an excellent background earlier that I'll add to, of why we're developing neuromorphic systems. So particularly looking at the AI energy problem and the kind of limitations of current hardware. I'm then going to introduce to you nanomagnets and why they're good for neuromorphic computing, and I'll show you some examples of the types of computing we can do with those systems. And then discuss some limitations and how we can overcome those limitations by making physical neural networks and interconnecting different systems together. So I think we're all aware of just how much AI is advancing at the moment. It's in the news all the time, but I think what's being increasingly spoken about and a concern is just how much energy AI is using. So just some small facts. 10 Google searches is the equivalent of energy or power consumption of running a light bulb. And ChatGPT, we're all aware of it, is actually using the same amount of electricity as 33,000 US homes. So this is critically unsustainable. But the trend is only set to continue. So there's a really good plot from OpenAI, which I'm showing here, which is illustrating the computing demands of AI over time. And so for a long time, the AI demands followed Moore's law. So the rate at which hardware could improve was increasing at the same rate that AI was improving. And so, it was all okay. But in these recent times, we're seeing AI doubling, the AI resources required doubling every 3.4 months. So you're getting about a 10 times increase in demand every year. And existing hardware is just not able to keep up with that demand. We're having to run our AI in data centers and consume an enormous amount of energy. I think Google have just announced that they're building nuclear reactors onto the sides of their data centers to cope with that demand. So all of this is ultimately coming down to the fact that in a conventional computer, you have a separate memory and processing unit. And so every time you want to do some data processing, you have to shuttle data between these two units, and that costs energy. And actually, I think something about like 60% of your smartphone battery is used just shuttling data. So what neuromorphic computing aims to do is combine these two units, so your memory and your processing, into one system and offload some AI type processing onto a kind of optimized system that has some brain-like dynamics. So there are many different flavors of neuromorphic computing, and we heard a little bit about the chip layouts. And so, there's a lot of effort, especially from big players such as Intel and Google and that kind of thing, to redesign existing CMOS architectures. But in the kind of academic world, there's also this physics-based neuromorphic computing. So really rethinking and redesigning the actual computing hardware itself. So an example of this is these memristor systems. There's a lot of excellent work going on there. We have optical computing. We heard a little bit about that just now. But we also have magnetic-based computing. So there's excellent work going on in the group of Julie Grolier, looking at MTJ-based computing. And what I'm going to talk to you about is nanomagnetic array-based computing. So what is a nanomagnetic array? So they kind of look like this, what they look like on the left here. You have a bunch of nano-patterned magnetic elements. So they're, around 600 nanometers long, 200 wide. And when you order them in an array, you get some interactions between the different elements, and that can produce some very interesting collective behavior. So people have been studying these things for a while, for things such as emergent phenomena like complex dynamics, as well as for computation. And so just to dive a little bit deeper about why these might be good for neuromorphic computing. So you can store information in the state of a magnetic element. So you can have things in these kind of macrospin or uniform states. You can also have the magnetization in a vortex state. And because they're close together and they're magnetic, you get some coupling between those. So you can do some processing of your memory state, directly in the array. And so what happens is when you pattern these things close together, these individual elements no longer respond individually, but they respond collectively. And so you get this collective in-memory computing. We design these things and we make these things lithographically, so you can really tune what your system looks like, the shape and the kind of arrangement of these magnets, and we can use that to control how well the computing does. And finally, these systems have resonant frequencies in the gigahertz range. So you can maybe imagine a scheme one day in the future where you could implement or integrate these devices into telecoms technology. So the dream of kind of maybe making these systems would be to implement something like a deep neural network, or maybe a spiking network or something like that. Whilst these software networks are incredibly powerful, they're actually very hard to physically implement. So in this neural network scheme, you have many different weights that you have to tune and reconfigure, and trying to map that onto a nanomagnetic array, for example, it's not an easy step. So what we did first is implemented a reservoir computing scheme. So in a reservoir computer, you still have a kind of network here with all these interconnections between various nodes, but you don't train any of the connections here. You initialize them randomly and they remain fixed. And the only thing that's being trained is this output layer. So this is very simple and cheap to do. And people have shown that these types of networks can be very good for time series processing. And so what I'm going to show you is how we took this kind of software scheme and replaced the software reservoir layer with our nanomagnetic device. So there are a number of requirements you need from your physical system. You need some kind of nonlinearity to kind of linearly separate a complex data set. You need some high dimensionality. So if you're giving an input into your system, it's got to generate a rich set of dynamics, and you've got to have a large number of outputs to help with your training. And finally, particularly for time series tasks, you want this history-dependent response, or known in the field as a fading memory. So the output of your system at a particular time not only depends on its current input, but also on previous inputs. And so what I'm going to show you now is how we managed to engineer this fading memory into our samples. So just to maybe go a little bit into the physics now, just to kind of give you a feel for what's going on. We have a picture, a scanning electron microscope image of our device on the top left. And we've engineered some of the bars such that they can be bistable in a vortex or a macrospin state. So they can, they can exist in either of these states and at the same energy. And what we see is that if we apply magnetic fields to the sample to switch our elements, we see, and you can these are real magnetic images of what the magnetization texture is looking like. You see these little kind of things that look like defects here, and these are actually the vortices popping in. And we see that as we keep applying magnetic fields over and over again, the same input, we're getting a gradual nucleation of these vortex states. And on the bottom here, I'm also showing the resonance spectra. So going back to that kind of gigahertz resonance I was talking about, and we can see that we can, as these vortices are nucleated into our sample, we're seeing a strong change in our dynamics, which we can detect. We can track how these state populations are changing over time. We see that they exponentially decay or increase. And so, we're starting to get a sense of the nonlinearity coming into our samples. Also, if we're switching from vortices back to macrospins, we get a nonlinear response. And we also find that the dynamics of these kind of states evolving really depends on its history. So what we've done in this right plot here is we've started our sample in a number of different magnetic states, so a different percentage of macrospins and vortices. And that's what the different curves represent. And then what we did is we applied the same input to all of these different states and watched how the state populations evolved. So we started off with a strong input, which caused this spike in the response. And then we started with a lower input, which caused the states to decay again. And we see that the rate of the decay on this exponential curve really depends on the initial state that the system was in. So we're seeing that we've got this kind of history-dependent response. We've got some nonlinearity arising. And now the question is, okay, how can we implement some computing? So in order to kind of get a reasonable computing scheme, you need a way of reading data out. And for a while, people were looking at these systems and thinking, okay, we need to know what the state, the magnetization state of every element in our array is in order to get the computational readout. But these images that I'm showing you, they take about 30 minutes. So, you can't use this as a computer. It's going to take you, it's just not possible. So what we did in our group is we decided to have a closer look at this resonant readout that I was talking about, and found that if you can probe the dynamics of your system, you can actually infer a lot of information about what's going on in the state without having to kind of take the full picture. And so you can have we can have a look at how this resonant response evolves. Here I'm inputting a sine wave into our system, and we're seeing at the bottom here the kind of dynamics evolving over time, and so we can use that as a readout for our state. And then there's a question, okay, you've got your data, you've input your time series that you want to, you've got your data out. How do we then convert that into a computational result? How do we get it to do some computing? And so it's actually a really simple step. We just use linear regression. So we'll take our data set like this, we'll split it into a train and a test data set. And then with that training data set, the goal is to fit a set of weights using ridge regression or linear regression or something along those lines. We're going to fit a weight to every one of these frequency values. And then if all goes well, we should have something that looks like this, where you have a target in black and you have a prediction from the array that's based on your experimental data in red. So just to kind of summarize that a little bit, we're inputting our data via magnetic fields. We're measuring the resonant response of the array as a readout, and then we're doing a simple, cheap software step to get the computational result. So now I'm going to go a bit into the computing and just to show you how these single arrays evolve. Here I've got 3 different samples. The kind of details aren't so important, but just so you're aware, we can really tune how these readouts look and the kind of non-linearities and the memories just by tuning our design of our samples. You can see these 3 different readouts are very different between these samples. And the first type of computing I'd like to show you is signal transformation tasks. So these are the tasks I'm going to show you are kind of benchmark tasks that maybe don't have so much real world applicability yet, but are really useful for kind of understanding what's going on. So the first is this signal transformation task. The goal here is you might input something like a sine wave, and you're going to transform that to a target such as a square wave or any kind of function that you want. So we've got our 3 arrays, and we can have a look at how they do at computing. So here's a particular target that we tried to transform it to. Here, the dotted red line is the target prediction. The prediction from the nanomagnets is in black, and then in blue, we show the prediction when you take the nanomagnets out of the computing pipeline. So really, all of the processing power is coming from the array itself and the array dynamics. And we see that different arrays perform differently, as you might expect. So we've got a very good array down here. But if we go to other tasks, such as this maybe slightly more complicated signal, we actually see that none of the arrays do very well. And this is actually a common theme in physical systems because your dynamics is hard-coded at the fabrication stage. The other types of tasks that we do are future prediction tasks. So here there's an equation called the Mackey-Glass equation. It was originally developed to model blood hormone levels. So you could imagine, you might have some wearable health device that is monitoring your signals, and the goal here is to predict future values of that time series. And we can have a look at how the computational error changes as we try and predict into the future. And so this is the 3 different error curves for the 3 different samples I showed you. And what you see is that, again, for some tasks, we find that the arrays predict very well, but for other future steps, the arrays don't predict well at all. And you might have spotted, actually, the arrays are doing better at predicting 11 steps into the future than they're doing at predicting 7 steps into the future. But that doesn't make much sense. If you're predicting the weather, it should be the other way around. It should be harder to predict longer into the future. So that's coming from the kind of crazy periodicity of the input signal, but it's also a sign that our systems aren't really doing computing that well. So the question is, can we improve? Can we take our samples and can we build something that can improve on this? So what we know is that our system is a recurrent system. It has some history-dependent response. It's very nonlinear and it's high dimensional. And so we can start to go back to our big neural network picture and start to think, okay, maybe we can actually use these different samples as nodes like you would in a neural network. So the first scheme we've tried was this kind of parallel input scheme. The goal here is you input your data into two different samples in parallel, and then you combine their output when you're doing the learning phase. And what we see is that when you do that, actually your performance gets a lot better. So here for this particular task, we got about a 5 times improvement in performance. But when we're trying to do the future prediction tasks, we don't see the same level of improvement. And that's because those tasks require a strong history dependence, and there's no way to improve the history dependence in this scheme. So we thought, okay, well, rather than putting them in parallel, let's try these series architectures where you take the input, you give it to one sample, you then take the output of that sample and feed it in as input to the next sample, and have a look at the results. And we also created these kind of larger analogous physical neural network type things where you're kind of really starting to create these more complex networks where you have many different samples and many different interconnections. And so we can have a look at how this does at the prediction task again. And so here in the black is the best single array, and the other curves represent different series networks. And what we see is that the MSE is really flattened, the computational error is really flattened, and we're starting to do some proper, future prediction now. We can have a look at animations. Hopefully these come across okay. In the top, we have a single array. Again, the target is in red and the prediction from the array is in black. You can see that the single array doesn't do too well. It's noisy, it's not really following the curve that well. Whereas for the physical neural network architecture, we're really getting very, very high accuracy. Now, that's all good. But one of the kind of promising things about neuromorphic systems is that you're able to train on your device. And maybe one of the use cases in particular for if you're in an environment where there's changing conditions, maybe linking this to the underwater robots, is that you might face a scenario where maybe your sensor breaks or there's a changing task that you want to do and you want to be able to rapidly adapt to that change in environment. Anyways, so I was just at this idea of if you've got a neuromorphic system, or okay, if you're in an application where you want to do some computing in a remote location, you might encounter a situation where there's a changing environment or changing conditions, perhaps a sensor breaks that you want to adapt to, perhaps the task that you want to do is slightly changed, and you want your system to be able to rapidly adapt to that changing task. So the goal that we tried to do is implement this idea of few-shot learning. So the goal here is that you set up your physical neural network in a way that it can rapidly adapt to these tasks. And we implemented two schemes. The first, the first is this rapid adaptability scheme. So we showed this the system just 50 data points of a new task that it hadn't seen before, and it was able to rapidly learn the dynamics of that equation and predict the future time steps. And we also tried this sparse data scheme. So we showed the system just 8 training points from this complex equation, and in just a few number of updates to the system's weights, it was able to adapt and learn this task. And just to show you, if we try that in a single array, it completely fails. So really, it's coming from the power of this kind of new physical neural network architecture. So far, I've shown you that the single arrays are kind of limited by their internal dynamics. But when you create these physical neural networks, you can enhance the performance and do things like few-shot learning. Now, that initial scheme was quite limited. We didn't do any training of the interconnections. So there's a question of, okay, can we create a trainable neural network? So the goal is this. We'll have maybe 3 different samples. They're all interconnected. You can arbitrarily choose these and you can train these interconnections. And in order to do that, we decided that we had to make a software analog so that the idea here is that we're going to make a software version of our network where we can train the neural network and then transfer the learned weights onto the device. So we have to know how the system responds to the current input and the current state. So like I was saying, the goal is to train what's known as a digital twin, where we would gather a bunch of experimental data, really use AI to learn the dynamics of our system in order to produce a software model. And I won't go into the details too much about how this works, only just to say that the model we developed very, very accurately matched the experiments. And it's really important that the software model does match the experiments very well, because otherwise when you transfer the weight from your software onto your hardware, it's going to, any differences in expected outputs are going to rapidly destroy the computational power. So here we have the experimental data and the model data. They overlap very nicely. So the goal here, okay, we're going to create this kind of neural network architecture, learn how to do a particular task in software, transfer the learned weights into the hardware, and then use that to test performance. And we've done a few different tasks. One of them is this sequential MNIST task, essentially a video classification task, where when we create a 2-layer neural network, we're able to get very low error percentages of about 3%. And we also implemented a neuroprosthetic gesture recognition task. So we got data from electrodes that are placed on your arm, and as you maybe clench your fist or wave your hand, the signals that the sensors read are slightly different. And so we input those signals into our device and trained it to classify what the gesture was. So what you can imagine is in the future is if you were to have a prosthetic arm, you could use these devices to convert electrical signals that come from your arm into the kind of prosthetic arm to mimic your hand action. And we also implemented a scheme called cascade learning. I won't go into the details of that, but we can do these regression tasks and these future prediction tasks very well to very high accuracy. So just to conclude, I'll wrap it up there. That I've kind of showed you that nanomagnetic systems are promising for the time series prediction. And that the physical neural networks enable this enhanced performance and this few-shot learning, and that we use a digital twin to train the physical neural networks. And currently, we're really working on miniaturizing our systems into devices. We've got some schemes in process to really drive down the energy consumption and increase the throughput of our devices. And then once we've done that, we'll be able to integrate those into kind of state-of-the-art devices such as these underwater robots or these neuroprosthetic things. Cool. Thank you very much.